Now then we just take cosine 45, which is, yes, 0.7071. And then multiply that by 100 times 100. Which give us 50 times the square root of 2, but I'm just going to write it out in decimal form. Erase that. Yeah, I've just got this leaning up against the wall. Very classy. Equals 70.71. Now that would be meters per second. Now let's say we want to take the velocity in the y direction. Well, that's just the inverse of that, which would be vi sine alpha, not cosine alpha, but sine alpha this time. So if vy equals vi, meaning the initial velocity that we throw it at, which would be 100 at this point, vi sine alpha, going to rewrite my vx equals vi cosine alpha. Now all we do is we take 45, factor that into sine, which I think is the same answer we got for cosine. I'm not quite sure, but I think it should be. So sine 45 equals, yep, it's 0.7071, and multiply that by 100 to get the same answer. So when you shoot it at 45 degrees, you get the same velocity along the y, you get the same initial velocity in the y direction as you do in the x direction. Just a little factoid there, you might find it useful. So at this point, it's 70.71 in the x in the y direction, and in the x direction, it would be 70.71 meters per second as well. Now you'll see if we change this to say 20 degrees, you should have a much faster velocity in the x direction than you do in the y direction, because you're not moving it up as much, I guess, if you want that kind of an intuitive look at things. So I can clean this up a little bit. As you can tell, this is very unplanned. Okay, there we go. Now, seeing as we've defined our parametric equation here, a very big word, not all that complicated. Geez, this is bumping this. I've actually got my laptop stacked on top of 2 boxes, which is stacked on top of a chair, a swivel chair. So this is not only perched rather precariously, but it tends to move a lot. So I'm going to try not to bump that again. So we've defined our parametric equation pretty well. We could also show this as a vector valued function, but I'm going to keep this as simple as I can. Now, we don't want to go into calculus 2 here. So if vy and vx equals vi cosine alpha, then, wait, no, sorry, vi of y, because it doesn't stay that constant velocity, because you know that the velocity changes, because once you get to the peak of this, or this apex of this parabola, if you throw it up, it stops, then comes right back down. You're subtracting gravity in that case. So what happens is v of t, you can extrapolate from this equation and the effects of gravity, v of t equal, or v at any point in time, that's what the t stands for, the subscript, equals vi sine alpha times any point in time. Because we have the velocity, and then if we multiply the velocity times the time, we get its point along the y-axis. Now, I really should write this on a bigger side of the board. I really need a bigger board, but I don't have one, so make do with what I have. Sorry, not v of t, y of t. Y at any point in time, I'm going to draw a little box there. So y at any point in time equals the initial velocity of y, which is equivalent to vi sine alpha times t. Now, without gravity, that would work, because we just throw it up and keep on going at the same constant velocity, just Newton's first law, I think. So if we multiply the initial velocity times the time, we have its position along the y-axis, but we have gravity to account for, so we're simply going, seeing as I choose this to be the positive side of the axis, so please don't throw any kind of a question like that at me. But what we're going to do is we're going to subtract it. So we're subtracting it because this is the positive axis, If it were the negative axis, we'd add it. But I choose this to be positive, and I have the right to, so I'm subtracting g from it, which gt squared. So y at any point in time, the y value of this little object here is determined by this equation. Y value at any point in time equals the initial this block here, the initial velocity along the y-axis, times the time, minus the minus 1g, or whatever the force of gravity happens to be in the place that we're at, times time squared, because a g is an acceleration, not just a velocity. It's a force vector. Once again, bumping my computer. Now the x-axis, actually, I probably should have started with the x-axis because it's so much simpler, but the, sorry, not v, x at any point in time equals vi cosine alpha. That's just the initial velocity along the x-axis times the time, because gravity has nothing to do with this. If there were air drag, then there might be some sort of minus and then some, integral here. But this is not calculus 2, nor is it advanced physics with air drag and lift. Now here is our second set of parametric equations, which we're going to be using very often, or at least throughout the rest of this example, or proof, I should say. I'm going to put these up here, actually. So y of t equals vi sine alpha, or rather fish, times t minus gt squared. You guys can see that, right? Okay, I think so. Now x of t equals vi cosine alpha times t. And I can erase this. Sorry, I would keep all this up on the board if I could, but I need more room to write. Okay, so I'm going to just redraw my axes here. Now, this would be like that. Line x. Draw a little box around this. Okay. So now we know, at any point in time, we can now determine the point that the object is at. So let's say I launched it at a velocity of, say, 100 and an angle of 45. We could factor this into these equations, find the x value, then the y value, and then show that as a coordinate point, x, y. Now, the x and y value would always change with time because it's dependent on time as determined by this equation. Simple enough. Hope you've got that. Hope I did a good job explaining it. Now, here's where it gets a bit trickier. If you've ever worked with this sort of a thing, you'll notice that this, seeing as you're subtracting gt squared, and there's only one gt squared value, or there's only one exponent in this equation, this is actually parabola. And if you know anything about parabolas, if you work with them at all, you'll know that parabolas are symmetrical, meaning at this apex here, this highest point along the parabola, or rather, if you were working with, say, fx equals x squared, it would look something like that. These are horrible axes, I know. It would look something like that. And then, just a second, I'm going to explain this a bit more in depth. Just to prove to you that a parabola is symmetrical, regardless of, what your parabola is. So you have, because the ideal parabola is just f of x equals x squared, which would look something like that, and that. Yeah, So at -1, you get 1. At +1, you get 1, 1. -2, you get 2, you get 4, sorry. At +2, you get 4. So you notice that it doesn't matter at what side of the y-axis I'm at, as long as we have this apex here, these two sides are always going to be symmetrical. They're always going to add up to the same.